So this month's education in chemistry is brought to you by the letter R for rust and C for continuity error, because I've got two amazing volunteers who are going to be joining me today. Unfortunately, they couldn't come at the same time, so you'll have to bear with me on the transitions. Right.
Where's my script?
You don't have a script, we're just talking.
Oh my god!
Okay.
Ion, electron.
Yeah.
I do remember. This is an ion.
My challenge is to try and explain this in such a way that anybody on YouTube hopefully can understand, although of course our audience is for other chemistry teachers. So I've given you a little sort of sheet to help you introduce you to some of the concepts that we're going to be talking about today, and on that sheet we've got some circles. Now these circles represent various different particles, and I've also got some magnets sort of representing those particles as well. And you can see we've got on our slide, and you've also got this on your sheet, some metal ions. In this case, the structure of iron metal consists of these positive metal ions, and we've also got these electrons that can move freely throughout the structure. And I'm trying to represent, by the size of these circles, how good these things are at holding on to or giving away electrons. So the smaller that circle is, the better it is at holding on to electrons. And I've given you like this sheet to give you sort of a warm-up in that respect. And I've got a little model here to sort of show. Here I've got my big circle and my model electron on it, and I've got my small circle or sphere. And of course, as I bring them together, what's going to happen to my electron?
It's going to jump to the small one.
Okay, so we move it across and there we go. So it jumps across to the small one. So my big circles donating electrons to the smaller circles. If we try and do it the other way around, electrons aren't going to be moving.
Gotcha.
Got it. Now, the size of the sphere or circle has got absolutely nothing to do with the actual size of the particles. It's just a model. Normally, if I'd be doing this, we'd be looking at this actually just using some numbers that we call standard electrode potentials. Okay. So let's see if this actually works. Which of these two things, the water or the iron, is better at letting go of electrons?
Water?
Okay, yeah, I'm just trying to represent it. So the water is better at letting go of electrons. In terms of what's going on with the electrons and the size of things, do you want to give me an idea about what you think might be able to happen?
I think that the electrons on the iron will move into the water.
Okay.
No, they won't.
Okay, so
they will stay there.
Okay, so yeah, so we've got here the water isn't as good at holding on to electrons, or the iron isn't good enough to letting go of electrons in this way. So we'll see what happens. You can see if we were to put a piece of iron into water, then we might imagine that some of these metal ions might dissolve right next to the surface into the water. And of course you can see here that because the electrons themselves, unless they react with the water, they can't get into the water.
Yeah.
So this ion has a positive charge, and the rest of the metal that's left behind now must have what charge?
A negative charge.
Negative charge, yeah, okay. And now, if we've got a positive ion and excess electrons, there's going to be a force between those, which is
Attracting.
Good, yeah. So this is not a process that can continue on forever. Okay, so what we're going to do is see what happens in a second when we try and sort of mix some metals together. So here we are, we've got this next slide here, and I've got a separate piece of iron on the left and some copper on the right. Which of the iron and the copper is better at giving away electrons?
At giving them away?
Yeah.
Well, the copper is best at holding on to them.
Okay, so both flip sides. So what we're going to do is we're going to see, like, same as before, maybe an ion might dissolve into solution, okay, and we might have some copper ions dissolving into solution, but because the copper is much better at holding on to those electrons, fewer copper ions will dissolve into solution. So now we've got, with an excess of electrons on the left-hand side, if we were to connect these up through a circuit, provide some like piece of metal wire or whatever, then there's an impetus for the electrons to start moving away from where there are lots of electrons, because the electrons are repelling each other. And that's the beginnings of some of our rusting type reactions. Numerically, if I was doing this with some of my senior students, I might sort of put these up. They represent the standard electrode potentials for the water and for the iron, and all these numbers are saying is that the iron isn't good enough at letting go of electrons to give those electrons to the water. So on the left here, I've just got water in with our indicator, and this indicator contains phenolphthalein and some of this orange stuff here, potassium hexacyanoferrate, and of course we've got like a nail, and wherever we see these blue ions that I've represented here building up into solution, we'd see a blue colour, and then the phenolphthalein is going to show any hydroxide ions, which we don't have here. So we've already said that the ion, this is a process that can't continue going, so if you want to carefully take just the white thing off the top there, hopefully we see there's nothing impressive happening in there, is there?
No.
Okay, so we've just got basically the solution. We're not seeing any pink colour, we're not seeing any blue colour, and that's telling us that without there being any oxygen in there, because this is water, distilled water on its own, there's no oxygen in there, that nail is not beginning to rust. And just for later on, would you possibly take a picture for us, just so that we can sort of include that onto the video? Setup, I've got some water that actually I've got the same indicator in, but this time I've used tap water and I've given it a good shake, and so there's going to be some oxygen in the water as well, and I've tried to represent that fact by doing my waters like I did before. Anywhere where we're close to the surface, there's going to be lots of oxygen coming in from the surface as well. So that's what I'm trying to show with that diagram here, where there is going to be some parts where there's not as much oxygen compared to other parts.
Okay.
Now, here, where there is oxygen, I've drawn these smaller circles to show that the iron actually now is able to give electrons, and that's what I've got our equation here showing. The iron is able to give electrons to the water and oxygen to make hydroxide ions. Okay, so if we let this sort of run, we can see we can't directly give electrons to the water unless there's oxygen there, but here we've got these smaller particles, or the smaller diagram showing that the iron now, in combination with oxygen, can give electrons. So if we watch what happens, we can dissolve an ion into solution, like we saw before, but now, whereas before there was nowhere for these electrons to go, okay, they can now be given to the oxygen and the water to produce hydroxide ions, and our indicator is going to go pink, in theory. And the key thing here is that the iron is going to be dissolving into solution in one place, and the hydroxide ions are going to be produced in another place. So we're going to compare the tap water one to the distilled water, and I don't know, we'll see, I literally don't know how far it will have gone by now. Again, not very impressive.
A little bit, you can see it a little bit.
In fact, if we take the lid off there, do you want to just tell people what we can see and maybe take a picture?
Yeah. I think we can see a little bit of purple, pink dots on the surface of the nail.
Okay, so we can see some purple. When you say so, we can see some purple. Can we see any blue anywhere?
Yes, just underneath.
Okay, so there's some blue there, and there's some blue on the end there as well, isn't there?
Yes.
And is the pink and the blue in the same place?
No.
Okay, so what's happening here is that electrons are being pushed through the iron and being given to the water in one place, and in other places the iron is dissolving into the solution. We can actually see that happening here. So if we can grab a picture of that, we can keep that for later. Thank you. Okay, so we've got our tap water now. We can see that that's starting to slowly rust. That iron, that blue stuff there is the beginning of the formation of the rust.
Yes.
Now, what needs to happen to allow this to continue is because this is going to start being like a circuit. We want electrons to be flowing through the metal here, out into the water here, and ions to go into the solution here. So unless we build up lots and lots of negative charge in one place, we have to allow the ions to be able to move through the solution and move away so that more electrons can go into that space.
Alright.
So one thing that we can do to try and improve the quality of this, effectively this is an electrical circuit we're making, is by improving the conductivity of the water by adding
Salt water.
so some salt to it. Okay. So our salt, okay, is going to add some extra ions in there that are going to help us to improve the conductivity of the solution.
Okay.
So in theory that would mean that our ions are going to be able to sort of move away and allow more processes to take place. Shall we have a look?
Yes.
Okay.
Ah.
So what can we see in here compared to the other one?
Okay, so on the one end we see some blue patches underneath, and on the other end we see some kind of pink red.
Okay, so in one place, if we could sort of go back to the previous slide, in one place we can see we're forming hydroxide ions.
Yes.
That's where the electrons are being given to the oxygenated water. And in the other place we can see the blue colour where that rusting is taking place.
Yes.
So actually the nail sort of rusts in one place, and here you notice actually this is actually by accident, not by design. You can see where the pink is occurring, the nail is sticking up slightly higher in the water.
Ah, yes.
And it's actually, so therefore there's going to be more oxygen on that end of the nail. So it's actually worked out quite nicely. Have we got a picture of this one yet? We'll grab that one. Sweet. Okay, so this is where we're going to start getting very interesting, because we've got two different things that we could think about doing to try and slow down the amount of rusting. We've already seen that putting in some salt is going to increase the speed of this thing. And what we want to try and do is say, well, can we protect our metal from forming this rust? That blue is a sign of something we don't want happening. That's our metal dissolving into solution and forming the beginning of the rusting process, I should say. So in these next pots we've got combinations of metals in different ways. Now you can protect, you might be familiar that in a tin can effectively you might have some steel, and we coat the inside of that metal in a less reactive metal, like tin. Okay, we don't have tin today, we're going to be looking at copper. And we also can try adding on a more reactive metal. Now what do I mean by a more reactive metal? If you just pass across the whole thing here, we've got some strips of magnesium in here, and you can see the magnesium is actually starting to sort of corrode in there, it's starting to look a bit skanky. And here we've got sort of a clean piece, and I'm going to put in some of our indicator solution. And almost immediately you start to see, we were yellow there, we're starting to produce what colour?
Pink.
The pinky colour. Okay, so the magnesium, okay, is immediately producing this pinky colour where our iron is taking a long time. These have been left here for about half an hour already. Now you might have seen that you've got a tin can basically coats the steel in a less reactive metal. And then another thing that we can do is something called sacrificial protection, where we can protect with a more reactive metal. Okay,
Yes.
so we're going to look into some magnesium and some copper today. So of these two things, like instinctively, okay, what do you think would be better at preventing rusting? Using a less reactive metal, like in a tin can, or a more reactive metal? Here we've got like a piece of magnesium that's sort of screwed into a larger lump of metal in a lock.
Magnesium.
Okay, what makes you say that? It's
I
okay, it's
don't
allowed to
know.
just be a guess. It's
I
just
don't
it's
know,
allowed
it's
to
my
just be a
guess.
guess. Okay, that's fine.
It's my
Okay,
guess.
so let's have a look.
Tin cans rust.
Okay, so you've seen tin can. Okay, right. So now here I've got another diagram. Remember that the bigger the circle is, the better that thing is at giving away electrons. Where are we going to get a sense of electrons trying to move?
from the magnesium to the iron.
That's exactly right. Okay, so the magnesium is going to be, there's going to be like a pushing force, you can think of it. The magnesium isn't as good at holding on to electrons, or you could think that iron is better at attracting electrons towards itself. And there's going to be this sort of pushing force from the magnesium onto the iron. We know that where we are actually sort of got lots of electrons, we might have a chance at giving those electrons to some water and oxygen combined. So this is where we've now got a slightly more complicated example here. Here's our magnesium in contact with our iron, and we've got our water and we've got our oxygenated water as well. We'll start, nice and simple, with just the magnesium and the water. In this case, I've given you this one as well to think about. Can the magnesium directly, forget about the iron, give electrons to the water?
Yes.
Yeah, it's also in my circle.
Larger in the circle.
Okay, so the magnesium can directly give electrons to the water. We can see that happening here. It's really quickly producing this pink colour. I didn't need to leave it any amount of time. However, it can also give electrons, as we've just established, to the iron. So there's going to be a pushing force of electrons through the iron. What's this going to do to the speed of the formation of our pink colour overall in here?
It's going to speed that up significantly.
Significantly. Okay, so we'll watch what happens. Electrons passing from the magnesium, forming a little bit of hydrogen gas here and some hydroxide ions, and pushing electrons in also onto the iron. I'll rewind that again. So we're going to form some pink colour here, pushing electrons across, okay, and up, and those electrons can be given to the water and oxygen together. So we're going to see pink colour all over the place, potentially. What do you notice about which ions have dissolved into the solution?
The magnesium is dissolved in.
Okay, and we only see the blue colour where we're dissolving iron ions.
Right.
So, when we look at this, what are we going to see?
Just pink, no blue.
So let's have a look.
Yeah.
Okay, so for the guys at home, what are we seeing?
A lot of red,
A lot of red.
but no blue.
No blue.
Hardly any blue, no.
Basically,
no
yeah.
blue.
Yeah, it's not really. Yeah, so loads and loads of pink there. Okay, so we're forming hydroxide ions all over the place, but our magnesium, as long as there's electrical contact there for it to push electrons onto the ion can't rust.
Yes.
So that's why we have these sort of things that we can actually screw into. In this case, the lock mechanism is constantly underwater, and as long as the magnesium is in a position to have electrical contact with it, the magnesium will sacrificially corrode, and then that can be replaced from time to time. There's actually a sign on here saying don't paint, because they actually want the magnesium to corrode for it to do its job.
Quite a lot of pink.
Quite a lot of pink, and certainly compared to here, a lot less blue. There's a tiny little bit. These nails have been used before, and one issue that you will actually have is that the magnesium, you try and get it on here, and if you try and squeeze it too hard, the magnesium just snaps. The copper is a little bit better for doing this, but I've got a life hack to sort us out from my final trick up my sleeve. So a lot of pink here, not very much in the way of blue. Okay, so inhibiting our rusting. Okay, strap in. We've looked at the magnesium, we're going to have a look at the copper now. We know that we can use, like tin, less reactive metals as well to protect our steel. But that will only work as long as there's a complete coverage. Okay, and we're going to see why that is. If you ever walk into a supermarket, you're going to find that any tins that have got dents in them, they go straight into the cheap aisle. It's not because they look damaged, it's because actually the contents themselves could be compromised. So let's see if we can work out how that's going to work in terms of where our electrons are going. So now from here to here, we've got our combination of our iron and our copper, where the electrons are going to be sort of being pushed.
From the iron to the copper.
Okay, now we're going to take this on, we're going to put it into solution. So here we are in solution, we've got our piece of copper touching our piece of iron, and again I've got my sort of oxygenated water around the outside of my droplet here. In terms of electrons, where are they going, remind me?
From the iron to the copper.
So it's from left to right. Now, as electrons move away from the iron, that is now going to leave us in a position where it's making it easier or harder for the iron ions to dissolve?
Easier.
Because as we're moving these electrons away, okay, what we saw before when the iron dissolved into solution, right at the beginning of that second slide or so, we saw that actually, unless we had somewhere to move those electrons, then that was going to rapidly reach an equilibrium. Now that we're moving electrons away, we can actually speed this up. So, watch the electrons, here they go, from left to right, onto the copper. Okay, from the copper, they're being deposited to the oxygenated water, and we're making our hydroxide ions. And at the same time, elsewhere on the metal, we dissolve in our iron ions, and we're starting our rusting process. So compared to before, is this going to be rusting more or less than the magnesium?
More.
Okay, we can see more blue. And
yes, it's very rusty.
okay, so we've got loads of blue here, and do we notice, is the blue and the pink in the same place?
No, separate places.
So if you look back to our diagram here, you can see here it's giving electrons to the copper is giving them to the oxygenated water, and so we can see the pink is actually forming around the copper. And then in a completely different place, here our iron ions are dissolving into solution and starting that formation of rust. Okay, so what do you notice?
Pink concentrated around the area of the copper.
Okay, which is exactly what we were expecting to see. And where's the blue?
At the distal ends of the nail.
Distal. Cracking word. Okay, so we've got a fair amount of blue kicking on there as well. This one is not really sort of Eva's one. It was absolutely kicking, loads and loads of iron ions dissolving to solution. But again, it's really interesting to see we've got the pink colour where we were expecting to see it. And I've got some little time-lapse footage of showing how quickly this actually will go. So, final trick up the sleeve. What we want to think about is what's going to happen if we've got a piece of magnesium in contact with some copper. The copper is then in contact with the nail. So what do you think is going to happen in terms of the rusting here? Is it going to be more rusty than either one of these, or what? Where do you think it's going to be on our scale of rust?
I think it'll definitely be more rusty than the magnesium.
Okay.
There's basically no rust here.
That makes sense.
Probably less than just with the copper.
Okay, because it could be like a mixture, because we've got iron, copper and magnesium.
Let me just consult my little sheet here. Everything's going to go towards the copper.
Okay,
and
so
from there they're going to go out into the pink solution.
Okay, so let's have a look. What do you notice is what's happening here?
There is a lot of pink surrounding the junction between the copper and the magnesium, and also quite a bit around, but not quite as much, around the nail.
Exactly. So what's actually happening here, you notice there's absolutely no blue, and before I said there's a little bit of blue here because it's difficult to get good electrical contact between the nail and the magnesium. Here the copper, I can really squeeze that in with a pair of pliers and get really good contact. Absolutely no blue going on here. These magnesium pieces are actually feeding electrons over, okay, directly reacting with the water, but also feeding those electrons over, and actually, even though we know that the iron on its own is not going to be very good at giving electrons to that water, we're seeing loads of pink colour there because of all of these electrons being fed over from the other side. And you can see here it's about electrical contact here because I've raised the piece of copper out of solution. It's all about where we're feeding our electrons. And if we wanted to keep protecting our iron, all we need to do is get a fresh piece of magnesium and replace the ones that are there already.
Yes.
Which I really love. I think that's really clever. But that's just me, maybe. Okay, so the question is, coming in like almost zero chemistry at the start of this, have we learned anything?
Yes. By putting more ions, more electrons on the nail, we can protect it from rusting because less of the ions will dissolve into the solution, therefore less rust.
The other thing, incidentally, I don't know if I give this one a little jibe here, can you see what's coming off on the magnesium?
Some bubbles.
Yeah, there's some bubbles there. So something to think about. If we have a look back at that, we see here, the magnesium actually is able to produce a gas. It's not really... Oh, you can kind of see the bubbles on this one as well, like just on there.
Oh, yes.
Yeah.
Oh.
Super sweet. High fives all around, I think. Thank you very much, Eva. High five. Let's cut it at that.
It's cool how it doesn't have to be covering it to protecting it, it just has to touch it.
Yeah, I mean, that's because it's about, you know, electrons, and yeah, like that is the thing. This one, with the copper, absolutely it has to be covering it. It won't work. The second you break that, though, you're going to be feeding the electrons in the other direction. But yeah, it's just that when you come back to this picture here, you see why they literally screw in a piece of magnesium, and they don't have to paint the entire rest of this is like a canal lock, and then they're like, oh, the magnesium stuff, unscrew it, screw in a new piece, and your lock is protected again. Just change it.